semiconductors, insulators and conductors and types of semiconductors. That means intrinsic semiconductors and extrinsic semiconductors. Intrinsic semiconductors means the pure form of a semiconductors are called intrinsic semiconductors. By doping or adding some impurities to the pure semiconductors, we can get the extrinsic semiconductors we can get. Then what is the difference between the, what is the comparisons between the extrinsic and intrinsic semiconductors? Let us see. Here the distinction between the intrinsic and extrinsic semiconductors means what is the comparisons and what is the differences between the intrinsic and extrinsic semiconductor. It is first of all intrinsic semiconductor. Intrinsic semiconductors. We know that what is intrinsic semiconductors? It is a pure form of a semiconducting materials with no impurity atoms are added to that, and it's an example for that the crystalline form of a germanium and silicon, means there is no any impurities in that matter, like pure water, that is also that does not contain any impurities in that. So here that it is a pure semiconducting material and no impurities are added to it. So example are the silicon and germanium are the examples for the intrinsic semiconductor. The next one is the number of free electrons in conduction band and the number of holes in a valency band is exactly equal. Both are in the conduction and valency band. We know that whenever if we take the diagram, then this will be the conduction band and this is the valency band. The number of electrons contained by the conduction band and number of holes in the valency band both are the same. Equal number of holes are conduction by the valency band, which is equal to equal number of electrons contained by the holes in valency band, and exactly equal to the very small indeed. Very small indeed. So that's exactly equal and very small indeed. So that's why here we can say that in valency band and at the same time conduction band, in the conduction band electrons and valency band holes are the same in intrinsic semiconductors. And also due to that the same amount of electrons and holes, there is a small conduction, electrical conductivity is very low. Electrical conductivity is very low, and whenever the electrical conductivity is low, it is a function of temperature alone. It is a function of temperature alone. If we give the temperature to that one, then some of the electrons will exist at a high temperature. They will move into the high energy levels. So this is about intrinsic semiconductors. If we compare with the extrinsic semiconductor with the intrinsic semiconductor, let's see. Here we said that the pure semiconducting material, intrinsic semiconductor is a pure semiconducting material, but in case of extrinsic semiconductors, here it is a prepared by doping, means by adding the impurities to the pure semiconducting materials, means like intrinsic semiconductors, means we are adding some impurities to the pure form. So that's why here it is prepared by the doping a small quantity of impurity atoms to pure semiconducting materials. For example, the silicon germanium crystals are doped with the fifth group of elements like impurity of atoms like arsenic, antimony, phosphorus, indium, boron, aluminum, like that elements which is added to the pure germanium and silicon atoms. Then we can find out the extrinsic semiconductors by adding the impurities also. If the types of impurities added, we can get the another types of semiconductors, that is p type of a semiconductor and n type of a semiconductor also by adding the impurities. Then if in case of pentavalent impurities are added to the pure form of a silicon and germanium, we can get the n type of a semiconductor. And trivalent means third group elements which is added to the pure form of a silicon and germanium. Third group of impurities added to the pure form of silicon and germanium. Then we can get the p type of a semiconductors, like that. Here is also these are the arsenic, antimony, phosphorus, indium, boron, aluminum. These are the impurities which is added to the silicon and germanium atoms. So then we can get the extrinsic semiconductors. So that's why it is prepared by the doping. by adding the impurities to the pure form of a semiconducting material. So the number of free electrons and holes are not equal in the extrinsic semiconductors because of we are adding the impurities. So that here is that the number of free electrons and holes is never be equal. There is excess of electrons in n type and excess of holes in p type. So earlier we discussed about the p type of a semiconductor and n type of semiconductor, the majority and minority charge gate. Then after this one we will discuss about the what is the difference between the n type and p type also. So here is that whenever we added the impurities, then we can get the excess of electrons or excess of holes in the p type or n type of, means here the excess of electrons in n type and excess of holes in a p type of a semiconducting material. So the why then we applied the impurities, means added the impurities to the pure form of a semiconductor, then electrical conductivity is high. Electrical conductivity is high. So here the electrical conductivity is high, so that's why here electrical conductivity depends upon the quantity of impurities added to the atoms. Impurity added to the pure forms, means if we add the more impurities, then conduction will be more, and it's a temperature dope, means here it is also depends on the temperature as well as it depends on the temperature and as well as whenever the quantity of atoms, quantity of impurities are added to the pure form of a semiconducting materials. So here is the comparison. It's a pure form, it is a doped with the pure form doped with the impurities, and these are the free electrons and free electrons and holes are same. Here free electrons and holes are not equal in extrinsic semiconductor. In conductivity is low in intrinsic semiconductors and conductivity is electrical conductivity is high in extrinsic semiconductors. So it is a function of a temperature, and it is depends on the temperature and as well as here the depends on the quantity of impurity atoms added to the extrinsic semiconductor. This is about the distinction between the intrinsic and extrinsic semiconductors. This is also one of the important question for the IP public examination for 4 marks. So this is about intrinsic and extrinsic semiconductors. After knowing the distinction between the extrinsic and intrinsic semiconductors, now we are going to discuss about by doping the pure impurities we can get the extrinsic semiconductors. By doping the pentavalent impurities we can get the n type of a semiconductors, and if we added the third group is nothing but trivalent compounds to the, then we can get the p type of a semiconductor. Then what is the comparisons or what is the difference between the p type and n type of semiconductor? In this case of this small comparison is there, n type and p type of semiconductors are both are type of a extrinsic semiconductors. It is also p n type is also extrinsic semiconductor, and as well as it is also an extrinsic semiconductor like this. Both are the extrinsic semiconductors. Because of by adding the impurities or doping the intrinsic semiconductors we can get the doping the intrinsic semiconductors we can get the values, means I can get the p type and n type of semiconductors like extrinsic semiconductors. So that the pentavalent or trivalent, whatever the impurities are added to the pure form, then only we can get the different type of semiconductors in extrinsic semiconductors. In that, what is the comparison between the both of them? So here it is that n type of a semiconductor, which is an extrinsic semiconductor, by adding the pentavalent or fifth group elements, by adding the impurity of fifth group elements, or these are also called as a pentavalent impurities added to the pure germanium and silicon, means here we are adding the pure germanium silicon materials to, we are adding impurities to this one. So that is a pentavalent impurities, like here whenever the impurities are added, then they provide the extra electrons in structure. Because of it is having that whenever we take the germanium and silicon, these are having the 4 electrons in the valence band. So valence orbital. So in the case of pentavalent there is also 5 electrons in the valence orbital. So 4 make the covalent bond in the germanium electron, and the fifth group element electron will form the covalent bond, and there remains one electron without any bonding, which is having already which is ready to bond with the another electron. So here the excess electrons can be produced in the structure in n type of a semiconductor material. So that's why the impurities of atoms added provide extra electrons in the structure. The extra electrons in the structure, already we did that. So whenever here if we take this, the phosphorus which is having the 4 and excess electron one of the 5. Here germanium having the 4. This is the neighbor 4. Germanium is having the total. Whenever the germanium or silicon shared their electrons to bond covalent to make a covalent bond and another remains one electron, the excess electron in the structure, it can be provide extra electrons in the structure are called this ready to donate the electron to another atom. The phosphorus which is excess free electron is there which is ready to donate to give the another bond to, it is ready to donate the electron. So that's why it is called as a donor atoms. Donor atoms in n type of a semiconductor which is the impurities added to that one, those are called as a donor atoms. So here it is the donors. Then so that's why here the excess electrons can be conduction due to the, it is ready to give an electron, donate the electron. So that's why it give the energy, it give the electrical energy to the another one. So that's why the conductivity is possible due to the electrons. Because of excess electrons is there in the n type of a semiconductor. So that's why here the majority charge carriers are electrons. The majority charge carriers are electrons and holes will be less in the valency band. So that's why we can say that holes are minority charge carriers. So holes is there but there is a electrons are more than the holes. So the density of electrons is more. Density of electrons in more in n type of a semiconductor if we compare with the density of electrons. So that's why the majority charge carriers are electrons and minority charge carriers are holes in the n type of a semiconductor. So here is the electron density, means the electron density is more greater than the holes density because of number of electrons is more. So that's why the density of electrons is also more. Then the donor energy level is close to the conduction band because of when here this is the conduction band and this is the valency band. It contains the more electrons in conduction band, holes will be less. The donor energy level which is close to the conduction band because of more electrons are there. So that's why the conduction band will be more close to this place. So here that far away from the valency band. This is far away. Forbidden gap is more between the valency band and the conduction donor level. And the Fermi level. Fermi level lies between the conduction band, donor energy level. Conduction band and donor energy level means between the Fermi level. Fermi level means, what is meant by the Fermi level? Every time we used to use the word Fermi level. What is Fermi level? So here it is that Fermi level is the highest energy state of that electron can acquire, obtained. The electron obtained. The higher energy state of an electron that can be obtained. As that whenever the temperature is increased, then there is electron also exist in the band. So that's why here that the Fermi level means the highest energy state level here that electron can acquire. So the Fermi level lies between the conduction band and the donor level. So that can be conduction is possible. So here is the donor energy level is close to the conduction band because of which is having the more electrons are there. So that's why the conduction band, the donor level will be near to the conduction band, and Fermi level which is lies between the donor energy level to the conduction band, between the donor energy level to the conduction band. So that's why here the donor energy level and conduction band. This is about n type of a semiconductor. If we compare the p type of a semiconductor with the n type of a semiconductor, just what is the comparison? As is this is also extrinsic semiconductor, as well as this p type of a semiconductor is also extrinsic semiconductor. Because of we doped with pentavalent, we get the n type of a semiconductor. If in case of we doped with the trivalent or third group elements which are in periodic table, third group elements are third group in periodic table, then the obtained by doping third group elements impurities to the pure germanium and silicon. the pure germanium and silicon is doped with the trivalent compound elements or the third group elements. Third group, by doping the third group elements it is also called as trivalent, right? So whenever the impurities are added, there is a lack of electron to make the bond with the neighbor germanium atoms. Means here already we did that one. Here germanium is there is a 4 electrons is there. Consider boron which is having the 3. So germanium is there, germanium make the, here is also germanium make the bond with the boron, and one of the lake there is no any electron which is ready to accept, which is ready to make the bond. If there is an electron, the germanium which is ready to accept means to make the bond to be stable. The boron require 1 electron, there is a vacancy for electron. There is a vacancy for electron, that is called as holes. So here it is that the impurities added create vacancies of electrons, that is holes. In the structure we got the sum of vacancy for the electron to occupy the electron which is ready to accept an electron. There is a hole, that is called as hole. So here it is that the impurities added create vacancies of electrons, that is holes. These are the holes in the structure and called as acceptor atoms. These are the acceptor atoms which is ready to accept another electron from another atom, which is a 3 valence in the boron. 3 valency electrons are there. There is a lack of 1 electron to make the bond with the neighbor germanium atom. So it is ready to accept an electron from the other atom. So it is also called, they are called as acceptor atoms in p type of a semiconductors. So here the holes will be more whenever we take the number of electrons. If we compare with the neighbor, there is also boron whenever we make the bonds with the neighbors, the number of holes can be shown. So that's why here due to the holes which is ready to accept the holes, ready to accept the electrons by the holes, so that's why more holes will be formed in the structure. So that's why excess holes will be in the structure. So due to the holes, the conduction is going on in the p type of a semiconductor. So that's why here the conduction due to the holes. That's why the majority charge carriers are here holes. The holes are majority charge carriers, and minority charge carriers are electrons. Minority charge carriers are electrons. So the hole density is, because of holes are more, so that's why hole density is much greater than the electrons density. Moles density is much greater than the electrons density. So that's why here the electron density is less than the hole density. So the acceptor level is close to the valency band because of holes are more. So that's why the acceptor, what is the border through the acceptor? This is the number of holes are there, so it is attracting more. So that's why accepting level is also near to the valency band, which is whenever electron comes to this place, and that can be accepted, not to reach the total valency band. It is electron is near to the valency band also, that can be attracted. So that's why the acceptor level is more. The effect of electrons is more because of it is having positive charge. If the positive charge is contained by the holes, p type of a, don't be confused, to better understand, to better remember, the p type means, p means positive type, positive means holes. We know that n type, negative electrons consist of negative charge. So that's why in n-type semiconductors, the electrons are majority charge carriers. Due to the electrons are majority charge carriers. So that's why that the donors level also will near to the conduction band because of electrons contained in the conduction band. So that's why the donor level is also near to the conduction band, and Fermi level also between the conduction band and donor level. Here then, though here n-type, in one word n-type we can remember everything. N-type means negative charge, N means negative charge, and as well as we can get that negative charge, and donor level is near to conduction band, and more electrons are majority charge carriers are electrons. Here is also p type of semiconductor. P type of a semiconductor means whenever the positive charge type of semiconductors. Positive charge means that is holes. Holes are majority charge carriers in p type of a semiconductor. Holes contained in the valence band. So that's why acceptor level which is near to the valence band. Acceptor level which is near to the valence band, and as well as the density of holes is more greater than the density of the electrons, and the Fermi level is lies between the acceptor energy level and valence band. Acceptor energy level and valence band, the Fermi level. The highest energy state that can be obtained by an electrons are called Fermi level energy. So this is about the distinction between the intrinsic and extrinsic semiconductors, and as well as the p type and n type of a semiconductors. There is a comparison and a distinction between the p type of, n type of, and intrinsic and extrinsic semiconductors.